Welcome back, class. We spent our last few lessons talking about the main ways to write quadratic equations. Today we're going to see how changing a quadratic equation changes its graph too.
Mr. Caldwell, did you happen to notice the very delicious looking red apple on your desk this morning?
I did notice it, Tom. Is it yours?
Oh no, Mr. Caldwell, it is yours, a gift from one of your very favorite students, who is a vampire.
Thank you, Tom.
One of your very favorite students who did not do as well as he had hoped on yesterday's quiz.
Tom, I'd be happy to talk to you about your grade after class.
Mr. Caldwell, I have an easier solution for you. I give you a little gift, you give me a little gift. We help each other out.
Tom, I don't accept bribes. Let's focus on learning today's lesson.
This guy drives a hard bargain.
We've already learned that what makes a quadratic equation is that its variable is squared. Y equals x is not a quadratic equation, but y equals x squared is quadratic because the x is squared. Now, quadratic equations can have other ingredients, like plain old x's and regular numbers at the end. But the only ingredient they must have is some amount of x squareds. So the simplest quadratic equation of all is just y equals x squared. You can think of y equals x squared as being the mother of all quadratic equations because we can create any other quadratic equation from it. We even have a special name for y equals x squared. We call it the parent function. And that's where we're going to start today, with the parent function. We're going to see how we can turn y equals x squared into lots of new quadratic equations just by making small changes to it. Then we're going to see how those small changes make a big difference with our graphs. So let's start with a question. This is the parabola for our parent function, y equals x squared. So who can tell me where the vertex or turning point of this parabola is located? Every parabola reaches a certain point and then turns around. So where's that point on this parabola?
The vertex of this parabola is located at the point 0, 0.
Good, V9. And since the vertex of this parabola is its lowest point, we also call it the minimum. The minimum, or vertex, of this parabola is indeed located at 0, 0. Remember, some parabolas don't open upward like this one. Instead of looking like a letter U, they open downward like a rainbow or a frowny face. An example would be this parabola. Even though it has the same vertex as our parent function, the point 0, 0, the vertex is at the very top this time, so we call this kind of vertex a maximum. For a second, let's just look at these two parabolas. In some ways, they seem like opposites. One opens upward, while the other opens downward. But in other ways, they're similar. They have the same vertex, and they have something else in common. You may have noticed in earlier lessons that some parabolas are narrower than others, while some parabolas are wider than others. These two parabolas, though, are equally wide. So the only real difference between them is that the second parabola is an upside-down version of the first, and that makes them a good pair of parabolas to start our lesson with. We know that our top parabola is the graph of our parent function, y equals x squared. So can anyone guess how we would change that equation to get this second parabola? In other words, what's the equation for the bottom parabola, since all we did was turn the top parabola upside down?
Mr. C, I don't think we know the answer. Can you give us a hint?
Absolutely, Ruby. Let's compare some points on our top parabola from our parent function with some points on this bottom parabola. On our top parabola, when x is 1, y is 1. But on our bottom parabola, when x is 1, y is negative 1. On our top parabola, when x is 2, y is 4. But on our bottom parabola, when x is 2, y is negative 4. If we keep comparing points, this pattern continues. In our parent function, all of the y values except 0 are positive. In our bottom parabola, all of the y values except 0 are negative. The values in our two parabolas are even exactly the same as each other at every point, except that the bottom parabola has a negative version of a number, and the top parabola has the positive version.
So,
It's like the top parabola and the bottom parabola have the same answers. Just the bottom parabola makes them negative.
Well then, if the top equation is y equals x squared, shouldn't the bottom equation just be y equals negative x squared? That would be the simplest way to turn all of our positive answers negative, wouldn't it?
That's exactly right, Codette. The equation for our bottom parabola is y equals negative x squared. And we just learned our first important lesson about transforming a parabola. If we have a parabola that opens upward, and we want to transform it into the exact same parabola that opens downward, all we have to do is multiply it by -1. This trick works with any parabola. It can even turn a downward-facing parabola back into an upward-facing parabola. This also teaches us something else. If we have a parabola that opens upward, like a smile, then its equation must have a positive amount of x squareds. If our parabola opens downward, though, like a frown, then its equation must have a negative amount of x squareds. We can remember this by thinking positive makes me smile, negative makes me frown. Now let's learn a second way to transform parabolas. Did someone just put another apple on my desk?
A token of my appreciation, Mr. Caldwell. You scratch my back, I scratch yours.
Cut it out, Tom. Stop playing that game.
Scratching each other's backs sounds like a painful game.
Vampires must not have long claws.
Class, let's refocus on our lesson. That includes you, Tom.
This teacher is a master of negotiation.
Let's go back to our parent function, y equals x squared. Here's our parent function again, and here's a new parabola. They both open upward. They both have the same vertex at 0, 0. But there's something that makes them different from each other. Can anyone see what it is?
The second parabola is very thin looking. It looks as if it has not eaten in many moons.
I get what you're saying, Wendigo. It looks skinnier.
So how did y equals x squared get transformed to create this narrower parabola? What do you think we could have done to our equation that would have changed our graph this way? Let's look more carefully. We'll compare points between the two parabolas again. On the parent function, when x is 1, y is 1. But on this new parabola, when x is 1, y is 2. On the parent function, when x is 2, y is 4. But on this new parabola, when x is 2, y is 8. The second parabola keeps giving us a y value that's twice as high as our first parabola. So what do you think is happening?
Since our parent function was y equals x squared, is this new parabola y equals 2x squared? That would explain why all of the answers seem to be doubled.
Codette, that's fantastic. You're really on fire today.
Codette is on fire. Do not worry, Codette. I will deploy my fire extinguisher.
No, V9. It's just an expression.
An algebraic expression?
Sit down, you overgrown graphing calculator. She means it is just a saying.
The English language is not logical.
Class, Codette was exactly right about our equation for this parabola. The only difference between our parent function parabola and our new parabola is that we transformed y equals x squared into y equals 2x squared. Common sense tells us that multiplying our quadratic equation by some number like 2 will make all of our answers for that equation get bigger. And bigger numbers will make our parabola rise faster. That's why this parabola looks narrower, or skinnier as you said, because it's rising so high, so fast. Now let's experiment with this idea for a second. What if I multiplied our parent function by an even bigger number, like 3, or 10, or even 100? What do you think would happen to our parabola?
It would rise even faster, so the parabola would look even narrower.
Right, Wendigo. And what if we did the opposite? What if we divided the parent function by a number like 3, or 10, or 100? What would happen to the parabola then?
I think it would get wider and wider and wider.
That's right, Bones. Dividing our answers would make our answers smaller, so the parabola would rise more slowly. For example, when we multiplied our parent function by 2, we got a narrower parabola. But if we divide our parent function by 2, we get this wider parabola. So, we've just learned how to make a parabola narrower or wider by multiplying or dividing the x squared. That's because anything that makes our y values get bigger, like multiplying, will make our parabola rise faster. And when our parabola rises faster, it looks narrower. On the other hand, if we divide x squared, dividing makes our y values smaller, which means they rise more slowly, which is why our parabola looks wider. Good. Now, let's try a combination of the two things we just learned. This parabola for y equals x squared divided by 2 is already wider than our parent function because it's divided by 2. But what if we also wanted to turn this parabola upside down? What would we do to the equation y equals x squared divided by 2 to flip its graph on its head so that the parabola opens downward like a frown?
To turn any parabola upside down, we just multiply it by -1. Negatives make the parabola frown. So wouldn't we just turn this equation into y equals negative x squared divided by 2?
Perfect, Ruby. The parabola of y equals negative x squared divided by 2 looks like this. And just like you said, it's the same as the parabola we started with. It has the same vertex, and it isn't any wider or narrower, but it's turned upside down because of the negative sign. Now let's add one final transformation. Let's learn how to move our whole parabola on the coordinate plane. In other words, let's see how to shift our parabola to a new location. The parabolas we've seen so far in this lesson have had their vertex at 0, 0. But parabolas can be located all over the coordinate plane. They can be farther to the right or farther to the left, farther up or farther down. Some parabolas are both, farther right or left and farther up or down. With these types of parabolas, it's as if we picked up our parabola and moved it so that its vertex changed from the point 0, 0 to some other point on the coordinate plane. But how do we change our equation to show that? Here's our parent function again, and here's the same parabola shifted upward. The only difference between this new parabola and the parent function is that the new one is shifted upward. So let's compare some points again. In our parent function, when x is 0, y is 0. But in our higher parabola, when x is 0, y is 2. In our parent function, when x is 1, y is 1. But in our higher parabola, when x is 1, y is up at 3. In other words, every time we check a value, our new parabola is exactly 2 units higher than the parent function. We're just adding 2 to whatever we got for our parent function. So, how do you think we would write the equation for our higher parabola?
Well, the parent function is y equals x squared. So if we add 2 to it, we get y equals x squared plus 2. Is that the equation of our new parabola?
That's right, Codette. Our higher parabola has the equation y equals x squared plus 2. Adding a number at the end of our parent function makes all of our answers that much bigger, which makes the whole parabola rise because all of its points are higher. In fact, adding a number at the end of any quadratic equation will shift its parabola upward like this. So we've just learned another trick for transforming parabolas. Adding a positive number at the end of our equation will shift our parabola up. So can anyone guess what we would need to do if we wanted to shift our parent function downward? What do you think is the equation for this parabola, which is shifted downward by 1 unit from our parent function?
Well, if adding a number to our equation makes the parabola move upward, then wouldn't subtracting a number from our equation move the parabola downward? If we want our parabola to shift downward by 1, wouldn't it just be y equals x squared minus 1?
Excellent, Bones. The parabola we see here is the graph of y equals x squared minus 1. So now we've learned almost all of the tricks for transforming parabolas. The only trick we still need to learn is how to move a parabola left or right. Let's do it. Here's the parabola of our parent function, y equals x squared, one last time. And here's a parabola that has been shifted 1 unit to the right. Its vertex is at 1, 0 instead of 0, 0. This time, instead of comparing points between them, let's just think for a second about what we're seeing. The two parabolas actually have the same pattern of y values. The y values go from 0 to 1 to 4 to 9 and so on. Those values aren't very surprising, since they're the numbers we get when we square x equals 0, and x equals 1, and x equals 2, and x equals 3, and so on. We get 0, and 1, and 4, and 9. The only difference between these two parabolas, then, is not the answers they're giving us. It's that the new parabola is doing something strange. It's giving us those same answers when we don't expect them. If we plug in x equals 1, our new parabola gives us the answer we would expect when x equals 0. When we plug in 2, the new parabola gives us the answer we expected for 1. It looks like whenever we plug in a number for x, we're getting the answer we expected for 1 less than x. We're getting the answer for x minus 1 instead of for x.
So, does that mean our new equation should be simply y equals x minus 1 squared instead of y equals x squared?
Tom, that's phenomenal. You're right. See, you don't need to bribe me with apples to do well in this. Tom, did you do this?
Mr. Caldwell, how do you like them apples?
Forget about the apples. Tom, you answered my question perfectly. To shift a parabola left or right, we change the number inside the parentheses, the number right beside x. If I want to shift the parabola to the right by 3 units so that it looks like this, I write y equals x minus 3 squared. If I want to move the parent function to the left by 2 units, what would I write?
You would write y equals x plus 2 squared, right?
Good, Codette. In other words, when we subtract a number inside the parentheses, our parabola moves rightward. When we add a number inside the parentheses, our parabola moves leftward. We've now learned all of our basic transformations. Let's quickly review them. We've seen how we can turn a parabola upside down by multiplying by -1, like when we transformed our parent function into y equals negative x squared, which flipped it from a U shape into a rainbow shape. We've also seen how to make our parabola narrower by multiplying by a number, like when we transformed our parent function into y equals 2x squared, and the parabola became skinnier. After that, we saw how to make our parabola wider by dividing by a number, like when we transformed our parent function into y equals x squared divided by 2, which made the parabola wider. And we just learned how to add or subtract a number at the end of our equation to shift our parabola up or down, like when we transformed our parent function into y equals x squared plus 2 to raise the whole parabola 2 units higher. Finally, we learned how to shift our parabola left or right by adding or subtracting a number inside the parentheses before the x gets squared, like when we transformed our parent function into y equals x minus 3 squared to move the parabola rightward by 3 units. Remember, a single quadratic equation might have more than one of these transformations in it, but now that we know how the transformations work, we can keep an eye out for all of them. In our next lesson, we'll learn some other important properties of parabolas, but for right now, I think we've done plenty for one day. Good work today, class. Make sure you do your homework, and I'll see you next time.